All right, everyone. So this is the last of the statistics lectures, and inferential statistics is actually one of the harder things to wrap your brain around. So I'm going to give you a rough outline of what it's trying to do and what questions are being asked. I don't want you to get too wrapped up in it. It is, as I mentioned, challenging. I have given out a cheat sheet for figuring out which statistical tests might be relevant for different types of things. And, it covers things like chi-squares and t-tests and regression and things like that. Excuse me. And I think that, when you're reading health-related research, that sheet will cover most of the major tests that would be relevant. And if you understand that sheet, then you should be okay for knowing most of what's going on. Now, in cases where you need to figure something out and it doesn't fall into those things on that cheat sheet, or you need more information about the details of it, well, you go and look it up, and that's exactly the same thing that I would do, and that's entirely all right. All right, so first I'm going to talk a little bit about inferential statistics in a more theoretical perspective. So inferential statistics is really talking about using quantitative information to make generalizations about the population based upon information from a sample that you've drawn out of that population. Now, again, these generalizations to these larger populations are always going to depend on how good of a job you did selecting your sample. So, if you select a sample that, of only Democrats, and then you ask about political questions and you generalize to an entire state, well, then you're going to have missed, Republicans or, people or independents or other folks. And you won't actually have an accurate generalization, even if statistically, based upon the population size, you have a fairly large sample. All right. So there's a few terms. Parameter, that's referring to the actual average score for that population. So if you actually took everybody in Washington state and assessed everybody's votes or how they would vote, then that would give you a parameter. All right. And that statistic is an average score that's obtained from a sample from that population. All right. So an example of this developing a statistic would be, okay, what can I infer about the average blood pressure, the actual parameter, after measuring the blood pressure in Washington state, after measuring the blood pressure of 350 randomly selected residents. So that's what we're trying to do with these inferential statistics. All right, so there's two major types of inferential statistics. One is estimation. So here we're trying to estimate how accurately does this statistic actually represent what we'd find in the overall population. And then the second type of inferential statistic is hypothesis testing. And that's where you're really saying, okay, given our independent variable, can we reject the null hypothesis that there's no relationship between these variables, all right? And that this hypothesis is actually supported in the study. Right? And those are two different types of statistics. I'm going to focus in first on estimation. So estimation has two types. First is a point estimate. So here we're just saying a simple value for the estimate for an overall population. So based upon our sample, for example, we estimate that the population parameter for female drivers is 18 years who get in accidents, for example. Okay. Another type of estimate is saying, okay, within that overall population, how confident are we? Where would we expect to see a normal range for that? So we might see for that, we might see a range of like, typically it would be 95%. So we'd say something like, based upon our sample, the population parameter for female drivers is between 16 and 22 years with 95% confidence that it would fall between those two numbers. Right, so that's a confidence interval, and almost always shown as a 95% confidence interval. There's always a 5% chance that it falls outside of that range, that the real parameter falls outside that range. All right, so let's go back to hypothesis testing. All right, so for a hypothesis, you have two different ideas. One is the hypothesis that you're testing, right? So that you actually propose. So I hypothesize that as smoking increases, lung cancer will increase, right? So that would be your H1 or your experimental hypothesis, right? HO is your null hypothesis, and your null hypothesis is that nothing is going on. So the null hypothesis in this case would be that there's actually no relationship between smoking and lung cancer, right? So remember, in science, we assume that the null hypothesis is true until we prove beyond reasonable doubt, or we indicate beyond reasonable doubt, that there really is a relationship between those two things. And usually what we see for a significance level is that 0.05, or about a 5% chance that there actually that there's no relationship between these things, but a 95% chance that there really is an association between these factors. All right. So typically what we'd see in this case is that if a p-value, which is this number, or alpha, is equal or less than 0.05, then the null hypothesis is rejected. All right. And the experimental hypothesis is accepted. So that indicates that yes, increasing in smoking does associate with an increase in lung cancer. Otherwise, unless we can say that its p-value is less than or equal to 0.05, we assume that the null hypothesis is true and that there actually is no relationship between the independent variable, smoking, and increase in lung cancer. All right, so one component to hypothesis testing is that there's two different types of error that you need to keep in mind, and one is type 1 error and the other is type 2 error. Now, type 1 error is the idea of the false positive, where your findings say that the null hypothesis is false, that we accept our experimental hypothesis, all right, false positive. And there's type 2 error, or beta, which is the false negative, where you say that there isn't actually a relationship even though there actually is, all right? So those are the two types of things. Now, typically for type 1 error, which is alpha, the cutoff is 0.05, and we measure that with a p-value, right? For beta, we talked about that a little bit in the sampling lectures, but that's really referring to power. So in studies, typically the cutoff for beta is 0.8. So in that case, it means that you have about an 80% chance in the study of, if there is a real relationship going on, if increased lung cancer really does increased smoking does really cause increases in lung cancer, then we have about an 80% chance of detecting it in a study. All right, so levels of significance. So, as I mentioned, typically the cutoff there, or the p-value, is 0.05, all right? So the idea is that if you do the study 100 times, we accept that, on average, we'd be wrong to reject the null hypothesis 5 times out of these 100 times, okay? 100 trials. Now, sometimes we want to set the level of significance to be more rigorous, all right? So we can also set the p-value cutoff at 0.01, or alpha at 0.01, all right? So if we do that, we have a smaller risk of rejecting a true null hypothesis. Now, sometimes we do this in situations where it's really important not to make an error about this. So if you have a drug, for example, that could potentially be lethal if it's used improperly, or used and it doesn't actually have an impact, you really want to be quite sure that it's really making a difference, right? So you might be more rigorous in those situations and put the cutoff at 0.01 to demonstrate confidence that there's actually a real relationship going on there. Okay. So there's a few things for thinking about these p-values in statistical tests. So for each of these tests that you're going to be doing for inferential statistics, and testing for testing hypotheses, you're going to get something, a p-value, right? So, the estimate that you get from this is the estimate that this happens based upon just chance alone, right? How likely is it that the results that you see are happening by pure chance, right? And that's ranging from 1 to 0, right? And the lower the number is, the less likely it is to have been observed by chance. So you assess the significance by comparing the p-value to the alpha that you selected, which is 0.05. If the p-value typically is 0.05. If the p-value is less than that number, you reject the null hypothesis. If the p-value is above the alpha cutoff, then you accept the null hypothesis, which is saying there's no relationship between the two. So that's just how you assess statistical significance. All right. All right. So what does this look like in a paper? Well, you might see something like, for a statistically significant finding, you might see something like African-American smokers have a 29% higher chance of developing bladder cancer per pack year than non-smoking African Americans, where the 95% confidence interval is 23 to 45, with a p-value of less than 0.031. And since it's less than 0.05, which is the common cutoff that's there, we usually would think of this as being statistically significant. Now, when you see a non-significant finding, it would be something like Caucasian smokers have a 23% higher chance of developing bladder cancer per pack than non-smoking African Americans. And there, the 95% confidence interval is 18 to 27, but the p-value is 0.112. So that's above 0.05. So we say we're actually going to accept the null hypothesis, which says that that this actually isn't a significant finding. All right. Now, there's an important thing that you should note, and here's the difference between clinical versus statistical significance. So, it's common in papers for you to read a paper and they make a big deal about the fact that they found a statistically significant finding. But, from a clinician's perspective, a statistically significant finding doesn't necessarily matter a whole lot. So let me give you an example of this. So imagine I was doing a weight loss intervention, and it's a year-long intervention where we do counseling with patients, where they do exercise for an hour every day over a period of a year, right? We do with 1,000 people, and after a full year of an hour each person of personal training time, supervised personal training time, we find that on average, this group of folks loses 1 pound. And because we have a huge sample size, we actually find that that is a statistically significant finding. So if I told you, well, we have this statistically significant finding, this intervention is a success, what would you say to me? Well, you'd say, well, it might be statistically significant, but you're nuts, right? Because, if people only lose 1 pound after, going through all this effort over an entire year, well, maybe it's statistically significant, but it's totally meaningless. It's not a useful intervention. In fact, it's a terrible intervention, right? So the point I'm making here is that statistical significance does not necessarily imply that you should care about the results of the study. What you really have to think about there is how much of magnitude is going on here? Is the magnitude of a difference significant that you actually care about what's going on, what they're actually finding in this study? And that's what we refer to as clinical significance. In other words, that this statistically significant finding is of a magnitude that you actually would care about it in a clinical context. So a way to think about this is we can use the forest plot that you sometimes see in meta-analyses. So if you look at this, you might find that, the first bar there is showing a result that is not statistically significant and not clinically significant. So there's nothing really going on there, right? Then you could have a result that is statistically significant, but not clinically significant. So that's the example of, having a statistically significant loss of 1 pound, but not necessarily reaching the amount that you would actually care about for an intervention of that magnitude, okay? So then you could also have a result which is not statistically significant. So you see a big range, but it possibly is clinically significant. And that might be something where, that's kind of interesting, but, we might need to do more research to say, all right, get a larger sample size so we can say, all right, is there actually something going on? And then Then we also have statistically significant results which are possibly clinically significant, all right? And then we have results which are clearly clinically significant. So for that last one, it's clearly above the threshold for clinical significance, right? So, these are things that you have to think about when you're reading studies, and to some extent, getting that threshold for clinical significance is something that, there's a range of different ways for thinking about it. Very often it's done by interviewing experts to say, okay, what would actually be a difference that would matter to you, experts or patients, such that we actually care about this difference. All right, so we're going to move on to actual tests of statistical significance. Now, again, these tests are actually really important because they are what allows us to say, all right, based upon, our best understanding and our, what we see in the data here, we actually think that there's a pretty good chance that there really is a connection between our independent and dependent variables, right? So there's two types of tests, and they're very distinct, and those are parametric tests and non-parametric tests. So parametric tests actually estimate a population parameter, and these, in order to do this, there's a few assumptions. First off, they have to be interval or ratio data, and this gets back to this to the types of data, the levels of measurement, where you really need to know what those things are to know which types of tests it's appropriate to use. The other assumption of parametric tests is that the data are normally distributed, okay? And if data is skewed, then the test might not be appropriate. Now, there are other tests that you can use, but you have to go into more sophisticated sort of statistical tests that we don't have time to go over in this lecture. Now, these parametric tests are preferred because they actually are more powerful. They have a better ability to distinguish significant results from non-significant results. And that's something that you want to do, if possible, in your studies. Now, you can also use non-parametric tests, and that's actually appropriate to all ranges of data, particularly nominal and ordinal data, or skewed data can sometimes can use these types of tests. And it doesn't necessarily expect that you're making estimates based upon population parameters. Now, these tests are very useful, but they're not necessarily as ideal because they tend to be a little bit less capable of detecting significant differences. But sometimes you have to use them because that's what's the type of data that you're looking at. All right. So within these different types of tests, there's also two different types of questions that you can ask. One is a test of difference, okay? Here's where you're testing whether, there's a difference between two different things. So, is one group different than another, all right? So, for example, if you're looking at one group, you might say over time, in a paired test, if you compare people before they're taught how to change bandages properly to after they're taught how to change bandages properly, do you find that their infection rates go down, right? So you have the same group of people, but you're saying before, what are their infection rates, and after, what are their infection rates? So you're saying, is there really a statistically significant difference based upon this intervention about teaching them about how to change bandages, right? Another example would be for two groups where you're comparing one group to another. So do people who are in a manufacturing job have higher rates of cardiovascular disease than people who have not been in a manufacturing job? So here you're comparing two different groups and you're saying, is one statistically significantly different than the other? All right. So these are, like I said, tests of difference between two. The other type of inferential statistic that we're interested here for hypothesis testing is assessing whether one variable varies or changes in relationship to another variable. So for an example of this is, what is the impact on weight when calorie consumption increases? So as we eat more food, do we see that weight tends to go up at the same time? or does it go down at the same time, or is there just no relationship whatsoever? So those are two types of ways of thinking about these inferential statistics. All right, so let's first talk about tests of difference for parametric information. Again, tests of difference is looking at, is this, are these two groups or two different factors in the same group different from one another, all right? So the most common one that we see here is a t-test, all right? And there, again, it's where you're looking at either two groups, like I described there, where you have people who are manufacturing jobs versus people who weren't, and saying, are the cardiovascular disease rates difference between those two, right? And that would be an independent t-test. Or, in situations where you're saying, okay, I did a teaching intervention and our infections rate different for this group before and after that teaching intervention. So that's a standard approach where you just be looking at using a t-test, all right? And ANOVA is another strategy, which is when you're looking at three or more groups, all right? So that's when you're saying, all right, so we have, one group where I taught them about, let's say we're comparing people who work in manufacturing to people who work in, tech industries, to people who work in academia, to people who work in hospitals. And we're going to compare those four groups and say who has the highest cardiovascular disease rate. Well, you can do that with an ANOVA. All right, so you can also test for difference for non-parametric data, all right? In situations where you're saying, are people who have brown hair different, viewed differently than people who have blonde hair, right? So that would be a situation where you don't have that sort of, any sort of ranking going on in those situations. So this is a very commonly reported statistic that you can use for a range of different non-parametric data, including nominal and ordinal data. All right. This this is typically represented as a chi-square, which is in papers an x squared. That's how it's represented. Now, something I would note here is there's another test, which is a Fisher's exact test. And the truth is that Fisher's exact tests are actually better than chi-square. It's just that a lot of people use chi-square because it's just used really commonly. The truth is that Fisher's exact tests are better. So if you see that, that's totally fine too if people are using that approach. All right. So then there's tests of relationship. And, the most common test of relationship is a test of correlation. All right. And this is looking at how much two variables are related to another. Do they go up together or go down together, or is there something else going on there? Now, this is usually used for, ordinal data or higher. You can use this for ordinal data. The way that we do this is visualizing it through scatter plots. I'm going to show some examples of that in a second. So the way that this is written is an R is the symbol, and I'll also talk a little bit more there as well. So sometimes correlation, I should note here, is also used for descriptive statistics in addition to inferential statistics, but you're not in those cases making inferences about larger populations. All right. So these are what scatter plots look like. So you have one variable 1 and variable 2, and you're sort of saying, all right, how do these different things vary together? So you have a bunch of data points for people. Say you're looking at, body weight and pull strength. All right. So here for variable 1, you might say, all right, we see that in variable 1, in plot 1, plot B. So in plot A, we're really seeing no relationship at all. It's just the data is all over the place. In plot B, we see as body weight goes up, pull strength goes up together. And so that's showing a positive relationship, all right? For plot C, we're seeing a negative relationship. So for example, as income goes up, maybe variable 1, income going up, the number of people's cavities might go down, right? Because people with more income might be able to get better dental care, okay? Plots D and E are, again, situations where, you're not really seeing much going on there in terms of relationships. And plot F is sort of a spurious correlation sometimes, where you can get some of these outliers that can sometimes result in you actually seeing correlations when there's really nothing going on there. So that's the value of actually looking at your scatter plots. All right, so reading correlations in papers. Correlations range from a negative correlation of 1. So negative correlation of 1 is that negative relationship. So the example there was income and cavities, right? To +1, where you have a positive relationship. And the positive relationship, again, is pull strength and body weight, right? You have more body weight, so you're more able to pull a weight of various sorts. Right, so if the R is 0, that means that there's really no relationship going on at all. If it's negative, you have a negative correlation. If positive, it's a positive correlation. If it's a perfect correlation, then you would see a number of 1 or -1. Okay. All right. Something that's important to note here, again, is that correlation is not causation. And again, significant results in general, even t-tests and other things, just because you're seeing that there's a difference doesn't necessarily indicate that it's proved that there's causation. Understanding causation is actually a very complex question with many different things that you need to demonstrate to indicate it. But we see lots of papers out there, showing that, as one thing goes up, another thing goes up, and therefore people say, this is, increased GMOs are increasing cancer rates, or whatever it happens to be. And I like showing this graph just because we see here, 2 statistics where you see, divorce rates in Maine and per capita consumption of margarine are incredibly high, have an incredibly high correlation. But, there's nothing going on. We have no real reason to think that there's actually a relationship between the two. If you look at enough things, eventually you'll find the correlation. And that's, just a caution there for reading these papers. All right. So there's another test for relationship, which is looking at regression. Now, regression, it sounds kind of scary, but it is amazing. It's really, really fantastic. It's a really helpful tool because it essentially does a similar thing to correlation, where you're looking at these relationships between things, but you can look at extraneous and confounding variables at the same time. All right. So if you're doing something like looking at there was these studies where we used to look at coffee, and they thought that, well, coffee, they were finding that coffee was really associated with, drinking coffee was really associated with cancer, I think bladder cancer, right? And they said, well, coffee causes cancer. And so people were stopping drinking coffee because they were really scared about this, right? Because there's a strong relationship. But they actually found that the real reason for this relationship is that people who drink more coffee are also more likely to smoke. And therefore, the coffee had no relationship at all with bladder cancer. It was just due to the fact that the people who drank coffee smoked more, right? And the real relationship was actually between the smoking and coffee. So what's nice about this is that in studies, what you can do is you can actually control for these other variables. So if you measure, how many people smoke, how many people drink coffee, and what the outcome is rates of bladder cancer, well, you can actually control, and you can say, okay, how much of bladder cancer is due to the smoking, and how much of the bladder cancer is due to the coffee drinking. And, if coffee actually caused cancer as well, we'd say, well, the smoking causes a lot of the bladder cancer, but maybe coffee would have some component of risk too. In this case, we found that there's no relationship. But it's a really valuable thing for our understanding of health, because we all understand that health is really complicated. We know that, most of these health outcomes, cardiovascular disease, cancers, the major causes of death in society, they have many different factors that are risk factors. And being able to piece out how much of a contribution each of those factors have in this health outcome is an incredibly valuable capacity to take on. All right, so there's really two types of regression that looks at these multiple factors to control for various different variables. All right, and the first is called multiple linear regression, and that's where you're looking at a dependent variable that is interval ratio data, and you're also looking at multiple independent variables that may be interval ratio, nominal, or null. Okay. And, this is typically shown with a beta. So you'll see that in studies. And that's essentially what the beta is doing is essentially describing the slope of each of these lines. Sort of like when you looked at the correlation and in the scatter plots, there was a slope there. It's sort of saying, as, income goes up, how much does cavities go down, right? And what it's doing there is essentially describing the slope of that line, okay? For the nice thing about linear regression is it also gives you an R squared. And an R squared is kind of a cool statistic because it tells you how much of the variability in this outcome, how much of the variability in numbers of cavities is due to income, and how much of it's something else. So other things might be how much sugar you eat or something like that, right? So saying, given what we've done in the study, we've been able to show that income alone explains 30% of how many cavities somebody has, for example. So that's a really important statistic for understanding these different factors in health risks. Multiple logistic regression is used when your dependent variable is dichotomous in terms of a yes-no answer. So did someone get assigned to the control group where they got this drug, or did they not, right? And you might have multiple independent variables in that situation. So, there your outcome that you're interested in is, or did someone get a disease or not get a disease, right? So that is, typically a yes-no answer, okay? Now this type of assessment is measured in odds ratios, all right? So odds ratios, there, no impact is a 1. 2 roughly equates to double the impact. So, smoking might, increased exposure to asbestos might double your chance of lung cancer. Whereas, protective effects like, telling people about how to change bandages might decrease a risk for developing an infection. Therefore, you might actually have a protective effect. So that might be an odds ratio of 0.5. Okay, so that's what's going on with logistic regressions. Okay, so here's sort of a flow chart for thinking about what different types of tests you might use for looking at different types of questions. So you can go into this first one is for tests of difference. So is it a test of difference? So are you looking at one group or more than one group? So one group, you have a range of different tests. If you have two groups, you have other types of tests, okay? If you're looking at a relationship, well, then you might look at the number of variables that you're looking at. And then for two variables, you might be just looking at correlation between, income and numbers of cavities, right? If you have more than two variables, then you might start thinking about regressions or other types of measures. All right, so realistically, in summary, how do you think about this when you're reading a paper? So when you're reading a paper, you want to pay attention to the types of data that's being used in that paper. Is it nominal data? Is it ordinal data? Or is it interval data, right? So this is going to imply what types of statistics you can use. The other thing you should really do is read the descriptive statistics and, think about them carefully. That's, you'll definitely see that in the demographics table, which is in most studies. And, that really helps you just get a picture of what the data looks like in the study. And that can be really helpful in and of itself in terms of just describing what's going on. then you also want to think, as you're reading about it, which variables are they talking about in this study? What, which variables are they saying is the independent variable, right? And once you go in and look at the paper, which ones did they actually show actually had statistically significant relationships and which ones didn't, right? So keeping track of those things is going to help you actually chart what's going on in the study. All right, so that's about it. Thank you for listening. And I hope that this was a little helpful for just getting an overview for what's going on with inferential statistics.